So today we are very happy to have Chrysa with us, Chrysa Avdellidou, for the monthly colloquium of the Hellenic Astronomical Society. So we are very happy to have Chrysa. I will say a few words about Chrysa. Chrysa graduated from the Department of Physics at the University of Thessaloniki, Aristotelio, in 2012. Immediately after, she started her PhD at the University of Kent in the UK, where she finished in 2016. And the subject of her PhD thesis was the hypervelocity impacts on planetary surfaces. Then immediately after, in 2016, she moved to ESTEC in the Netherlands, Noordwijk, as a research fellow, where she worked for 2 years. And after that, she obtained a fellowship at NIS Observatoire in France. She will be in NIS until this summer. And after that, from September onwards, she will move back to the UK, where she has received a permanent post there as a lecturer in planetary science. So congrats, Chrysa, for this achievement, because you are quite young for getting a permanent position abroad. Just a few words regarding the missions that Chrysa is involved. So she's a collaborator on the NASA Osiris-Rex Sample Return Space Mission. She's a member of the ERA working group 4 on data analysis, exploitation, interpretation. She's a collaborator on the JAXA Thermal Infrared Imager instrument on board the same mission, HERA. And she has been a coordinator of international team for lunar impact detection and crater discovery, the Lunar Reconnaissance Orbiter. And that's only a few achievements of Chrysa. She also has quite a large number of research grants. And today, Chrysa we'll talk. Just a second. I now have to switch to another screen. Sorry for that. So Chrysa today will talk on. Hold on. I'm sorry, I'm not very well organized. Okay, the title of the talk is Meteorites that built Earth reveal the Earth stages of the evolution of our solar system. And so now I give the floor to Chrysa. Thank you, Chrysa.
Thank you very much. Thank you for saying that I'm young. That's great. So this is what I keep. So thank you very much for this invitation. I tried to put together a few slides in order to present 2 of our latest works that we have done here, mostly in NIS. One of this work is already published, the other is under review process, but both are combined in the same framework. So I tried also to, let's say in this talk, I tried also to give some basic concepts of what I will talk about. I understand this is a virtual talk. If I was there in person, I really have no problem. If someone doesn't understand something and would like to ask a question, for me, it's fine if you want to open your mic and ask the question while I go. If this is fine with the organizers, to have a good flow for later for streaming this talk. So it's up to you. So, okay, it's better to start. It's getting a bit late. The targets of this research that I will present today are the small bodies of our solar system, and where I study the impact processes on them. And as we can see, the impacts play a role throughout the story that I'm going to tell you. Impacts are responsible for the formation of the small bodies by accretion of their constituents, their disruption of the small bodies and the formation of what we call families of asteroid fragments, the cratering on the planetary surfaces and of course on the surfaces of the small bodies, as well as the material mixing, so different impactors that they have different materials, they hit a target and then we have a mixing of materials that they actually were formed in different reservoirs in the solar system. This is something that we start to see slowly. And also from those collisions, small pieces are generated, not only larger asteroids, and these can reach the Earth ground and can be found later as meteorites. Now, for this specific work that I will show today, we used a multidisciplinary methodology where we combined spectroscopic observations, modeling, but also we used meteoritic data from the literature. So really we had to put together different, let's say, little disciplines inside astronomy in order to reach our result. So first things first, let's go a step back and see the planetary formation from far. One of the fundamental questions in planetary sciences is how the planets form directly from the protoplanetary disk. The evolution of the protoplanetary disk has 4 stages. We have the initial molecular cloud that collapses, and we have the disk formation with the physical and chemical evolution of the disk. We have then the formation of the first bodies directly from the disk that we call them planetesimals. This is a term that I will use throughout this talk. And then we have the dispersal of this nebular gas, and the later evolution of the system. Now, today we have reached a level where we can see the very first stages of the planetary formation in a numerous protoplanetary disks around other stars. For example, they do this research a lot with ALMA. Also, we can understand the results of the planetary formation in our own solar system by studying our planets, but also thousands of exoplanets around other stars. However, the stages of the planetesimal accretion, these intermediate stages, directly from the protoplanetary disk and before the formation of the planets, is still a bit hidden from our telescopes. So we really try to use different approaches and understand what are these first bodies, how they evolved, and by studying them, what they can tell us for the formation of the solar system, because they have witnessed dynamical and collisional history of the solar system. Now, in our protoplanetary disk, planetesimals were formed at different heliocentric distances and with different compositions, as we can understand. For example, we can have a planetesimal, let's say with bright albedo, as I painted here, that formed directly from the protoplanetary nebula. Then we have another planetesimal, a third one in larger heliocentric distances. I painted a bit, it's a bit darker, so it is more primitive, very low albedo, and so on. Due to dynamical processes that occurred in the early phases of the solar system, the planetesimals from the terrestrial region, as well as from the outer solar system, were implanted to the asteroid belt. I will talk about that also towards the end of this presentation. And there, due to the multiple collisions, we see that, for example, the bright planetesimal that was formed in small heliocentric distances broke, created a family of objects. This one didn't break. Maybe we can still find it today. It's a surviving planetesimal. Another one, dark, also broke, created its own family in the main belt. And then due to, with time, the orbital elements of the family members diffuse in semi-major axis and generally in their orbital elements. And then these families start to overlap. So we don't distinguish them very much. Not only the families overlap one to the other, but also they hide the original unbroken planetesimal. So it's a big field here of study to understand what is first generation, what is later, what information we can get from these guys. Now, another introductory slide. Let's focus now our story focuses now in the asteroid belt. So this is the view of the asteroid belt. We have the semi-major axis versus the proper orbital inclination. Each one of these dots is an asteroid, and each asteroid is characterized by a big set of physical properties. It has its orbit, diameter, mass, rotation period, albedo, has its own spectrum, and several other parameters. In this plot specifically, I painted each one of the asteroids with a different color, as you can see the color bar, and this is used as a proxy of its composition. We can see that the composition varies, and the main belt coexist dark carbonaceous bodies, which are primitive and arrived in the belt from larger heliocentric distances. They were formed beyond the orbit of Jupiter. And we also have the stony ones that represent objects that they were formed in the solar system, some together with the terrestrial planets and maybe some in situ in the belt. We can also beautifully see that the high density regions that correspond to, these are the regions that correspond to the asteroid families, and they were generated after the collisions that I mentioned before. And asteroid families appear as clusters of objects in the orbital element space, in major axis, eccentricity, and inclination. And this characteristic also has been used so far by traditional techniques, clustering techniques, in order to discover new families. However, very old families are so diffused that it's very difficult to be found, to be detected with these classical approaches. As I mentioned, one of the most important physical properties of the small bodies that allow us to have a first proxy to their composition and start to distinguish them are, of course, the reflectance spectra. So this is a card, this is a summary of the spectral types that we use. This is the most up-to-date taxonomic scheme, we call it BASDEMEO, that we use in order to characterize and classify the spectra of asteroids. These are divided into 3 main complexes. We have also some end members, and each one of the complexes, it has other types inside with small differences in their features, in the slope and also in absorption bands. So just to give you a very brief idea, the S complex asteroids are the stony ones, the ones that they were formed in the inner solar system. C complex ones are the most primitive, darker asteroids that they were formed in the outer solar system. X complex can have everything, can have metallic asteroids, mesosiderite, so 50-50% stony and stony and metallic. It can have enstatic materials like the one that Earth accreted, so similar material, Earth, Mercury, and so on, and maybe some also carbonaceous. So the X complex, as you understand, we call it X because it has a bit of everything. So we try to disentangle this group. And of course, some end members, for example, the A-type asteroids, they are probably mantle of some very old planetesimals, so they are full of olivine. And like this, we try to understand the composition. Now, another characteristic that I mentioned before of the families is that when we have a collision in the main belt and we have the first cluster of fragments of family members of smaller asteroids, they don't stay there forever. Due to non-gravitational forces, the asteroids, they start to drift in the semi-major axis. Here is a diagram 1/d. D is the diameter versus semi-major axis. So we can see that the smaller asteroids that are at the top of the V, they drift faster right and left. Of course, if they're prograde or retrograde, so it depends how they spin around, they go to the 2 different directions. Anyway, and so as you can understand, as the family, an asteroid family, ages, this initial V shape starts to open because the asteroids drift. So this V shape is a characteristic that we use now the recent years, apart from the classical clustering techniques, in order to discover new families in the main belt. And we have discovered actually very old ones, where other traditional techniques start to, let's say, to fail, to be more tricky to do the job. Now, as the small fragments from a family, the small asteroids and the little fragments, they drift from the breakup point, they can reach what we call the gaps in the main belt. So the places where we have the resonances with the planets, and the most effective, and this, when an asteroid then drifts and can fall into these gaps, can actually be ejected from the main belt and reach the near space, collide with Earth, collide with the Sun, can do several stuff. So the most effective resonances is the 3-to-1 between the inner and the central part of the belt, and the mu6 secular resonance, both of them, you can see them here. So the inner main belt, which is surrounded by these two resonances, feeds us with a lot of near-Earth asteroid and smaller fragments, whatever is smaller than 1 meter. We start to call it meteorite. So therefore, there are too many routes to receive meteorites to Earth. First of all, we need to have a large collision in the main belt, so we need to create an asteroid family or a large cratering event at least. So a big collision that creates a big basin on the parent asteroid and thousands of fragments. And then small meteoroids via the resonances that I just showed can arrive to Earth directly, or with the same dynamical mechanism and path, small asteroids, hundreds of meters, kilometer, and so on, they escape from the belt, become near-Earth objects, and which may also fragment and deliver small pieces to Earth. So we have also some examples from that, but it's not now at the point to discuss this. Now, as we understand, nature feeds us with free samples of solar system materials. However, Earth, fortunately and unfortunately, has atmosphere, which can play a negative role for the selection of the meteorites that we receive, because the meteoroids, let's say, that they come for the more primitive carbonaceous asteroids are probably the weakest, they are most fragile, so they don't survive the entry. So they are burned in the atmosphere, usually at a very high altitude, and we don't receive them as meteorites. We receive, of course, a lot of them, but not as many as we should. So for sure, we have a selection bias in this respect. That's why they sent €1 billion space missions, $1 billion, sorry, space missions to go and sample two near-Earth dark primitive asteroids, Bennu and Ryugu. Bennu was visited by NASA OSIRIS-REx, that cost about 1 billion. Japan built something about 100 million spacecraft and sent it to Ryugu. They both did a similar job. Of course, the American mission had very high, let's say, great images that we could do more things than we could do with the images from JAXA, but they both did great work. They both sampled. We already have the sample from the Japanese, from JAXA to Earth, and they have already published their first papers where they found organics and so on. We are still waiting the sample to arrive this September from the OSIRIS-REx to Earth. But this is a full story for another talk next year when we have also these results. So this is a scheme of the meteorite types that we have collected and we've studied so far. The game here that we play is that we try to link these meteorites with the specific parent bodies. Because we have the meteorites, we put them in the lab, we understand their properties, their materials, how old they are, probably where they formed, and so on. So if we try to link them with a specific parent body, means a specific family or something like that, means this will allow us to characterize a large population of asteroids, all the fragments of one family. It's like we look inside into this first generation of planetesimals, how they were before they broke, and so on. So another, let's say, how can I phrase that? Another type of planetesimals. So when the planetesimals were formed directly from the protoplanetary disk, some of them, the ones that they were formed at the very, very early stages. So let's say between the first one to 2 maximum million years after the formation of the solar system, they had incorporated a lot of aluminum-26, and this, with its decay, increased the temperature inside, and because of this increase of the temperature, it started to differentiate, so to create layers. So a general, let's say, idea that we have for a differentiated planetesimal is that we have maybe an iron core, an olivine mantle, and the crust. Is like more or less what we see on the asteroid Vesta, that it was visited by the Dawn space mission. Of course, we haven't seen any core or something, but we understand it's differentiated due to the composition that we see on the crust, and of course with the link with the meteorites that we have. However, apart from that, it's not very clear if we still have planetesimals that they were really differentiated. So this is one of the, let's say, of the important questions that we have to answer in the near future. That's why also NASA has another space mission that goes to asteroid Psyche. They believe that it is an exposed metallic core of a planetesimal that was differentiated, and then somehow the mantle and the crust via impacts they went away. Maybe it's this, maybe it's just a mesocytherite. We're not very sure. The launch had a delay about a year for some technical issues. So we still have several years ahead of us until we understand what is Psyche. Now, the study of the meteorites also show us that we have an isotopic dichotomy in the planetesimals in our solar system. In one side, as I mentioned a lot of times so far, we have the terrestrial planets and the non-carbonaceous chondritic planetesimals, and on the other side, we have the carbonaceous chondrites. Those two groups of meteorites are made of different materials, and either they accreted at different times in our disk that was changing in composition dynamically, or they were accreted at different places at the same time in a heterogeneous disk. Our latest notion is that the planetesimals of both times, they were accreted at the same time, contemporary, in the two different locations in the solar system. And one of the studies shows that the internal heating of the planet, how can I say, the internal heating of this first generation of planetesimals occurred in both reservoirs. So we should expect to see differentiated planetesimals not only from the inner solar system, but also from the ones that they were formed in the outer solar system, and they have this primitive carbonaceous composition. They have found iron meteorites that when they studied, they said, this iron meteorite comes probably from a core of a differentiated C-type carbonaceous primitive meteorite. So, but still we haven't discovered a family that shows this, the hints of such differentiation, and this would be something very cool to do in the future. There is one potential family I will mention in a while that we are doing some spectroscopic observations this year. I was very happy to get some time and really hope we can find one of these families. If it is, it will be the first one of its kind. So we are very happy. In general, we can link the ordinary chondrite meteorites, they look like some of them in this photo, with the S complex asteroids and the carbonaceous chondrites with the C complex asteroids. These are very big general associations, but we haven't pinpointed specific meteorites with a specific parent body or parent family. We have so far two, let's say, definite links. One is the type of meteorites that we call obrites, that they were formed in the terrestrial planet region, and they come from the asteroid family of Hungaria. And then we have the HED meteorites, that they come from the asteroid Vesta and its family. Asteroid Vesta had two big impacts that created the two big basins that they were discovered on the surface, Venenei and Rea Silvia, at 1 and 2 billion years before our time. So these meteorites definitely come from this body that we think it is also differentiated. So this is a unique source. Only for two. From all this group that I showed before of this big tableau, only for two. This is the location of the Hungaria family and the Vesta family in the inner main belt. Now, what was the point of our project? Having all this in mind is that what we want to do is that we want, first of all, I'm sorry, we have to discover new families. We have to use all the modern techniques that we have developed the last years in order to discover new families, young and old, try to link them with known meteorites. And to do this, we had to do a very important data mining. We needed to have really all the possible physical properties that we could for million asteroids that we know so far in the belt. We need to do targeted extra spectroscopic observations on objects of interest when we think that we have a hint that we have found something. And of course, we have to do modeling. Modeling means everything. Model everything. So, and actually, this is what our team did. We had a grant from that. The PI is here, my colleague Marco Delbo. So we had a big grant where it was actually, that was our project, to discover old families, characterize them, find the equivalent meteorites, and produce unique links, and see if this, we can put them in the general framework of the evolution of the very early stages of the solar system. As I said, the S complex asteroids, they are connected roughly with the ordinary chondrites. There are many subtypes inside the C complex with carbonaceous. We didn't try to find links in these two big groups because they are very big. We have a lot of families from both groups, a lot of meteorites from both groups, mostly from the past one, with very small differences and so on. So we said, let's start from something maybe that it is more clear at the beginning to see that our methods work. So we started from the X complex. As I mentioned before, the X complex is very degenerate. So you can have different, a plethora of materials, from carbonaceous, that they were from a totally different place, down to enstatites, that they were from actually here, around 1 AU. So we focused on this X complex. So what we did in our work is that we wanted to find the source of a specific type of meteorites that we call them enstatite chondrites. They have two types. They are called EL and EH. They are the same in number in the database of meteorites. And they should originate also from two different parent bodies. So we should find two different big collisions and two main sources for all the meteorites, all the enstatite meteorites that we have now in our collection. So we try to see, can we find at least one, what is going on here. Also, the enstatite chondrite meteorites, they are characterized by medium albedo values. So they are not very bright, but also they are not very dark, like the carbonaceous one. They're not 5, 6, 7% albedo. So what we did is that we went first in the literature, what has been published. And we spotted that there in the literature, they are mentioned that they are about 18, not about, exactly, 18 families in the main belt that their members could belong to the X spectroscopic complex. So they could be parents of enstatites, but still we have to study. So studying more, we saw that the three of those families, they had already characterized into details by dedicated spectroscopic observations. One actually, it was the family that I showed here, the obrites. These are enstatite achondrites, another type. And the other families were finally irrelevant. They didn't belong to the X complex. One was S type and the other was C complex family. Also, from the remaining, the majority, they were very dark. So you see the medium geometric visible albedo of their members was less than 8%. So they were very dark asteroids. So they couldn't be connected, at least on this physical property, with the enstatite meteorites that can have 15% albedo, 16, 19% albedo. And one of those, the family of Calliope, it was very recently shown that one of the biggest asteroids in the main belt that's called Calliope has a family. There was a family, they connected to this parent body, and now we are doing the spectroscopic observations to see, this is probably the potential one of the differentiated family that has iron core and so on, that belongs to the carbonaceous guys. So we are not talking also here about enstatite. So by killing all these families from our data set, we resulted only with 2 potential candidate families that could send to Earth enstatite meteorites. These are named Hathor and Zeta. They were discovered here by our group in Nice. We published them in 2019 by using what I mentioned before, the V-shaped technique. They're kind of old family, so Hathor is about 3 billion years old, and Zeta can be as old as the solar system. We're talking about a very old impact in the main belt. Both they have medium albedo values, and both probably belong to the X complex. We didn't have much observations, maybe a few spectra in the visible range. That's why we said, okay, we have to go and characterize them. So what we did is that we wrote proposals one after the other. Sometimes we got time, sometimes we didn't get time. This is life. So I started observing this for this work since 2017 when I was still at ESTEC, and I finished observations 2021. I'm sorry. So we used different telescopes. The majority of the observations were done at the NASA IRTF, so the near infrared range, which is very diagnostic for this type of materials. Of course, we had some other auxiliary observations in the TNZ and also at the LDT Lowell Observatory. And we got from the literature visible data, a lot of visible data that they were available, and of course spectrophotometry from Sloan Digital Sky Survey, from SDSS. So this is how the spectra more or less look like, and actually we got what we thought at the beginning. We were lucky, to be honest, because I always thought I would like to find the source, and finally everything worked, and we saw what we wanted to see. It's not always the case. She said you don't see always what you want to see, but here we were lucky, to be honest. So we characterized both of these families. We saw, as you can see in the plot at the bottom, that the families, they are not identical. Actually, they are different in their spectra. Maybe for you, that you're used maybe to others, but you think that they are the same. No, they are not the same. The slope is totally different. The spectra of Zeta, the black spectra, they have also a small band at 0.9 microns, which is not so much the case for the red. It means they have maybe pyroxene inside and some stuff. So this distinguishes the two spectra. Also, we calculate the average albedo for each one of the families, and of course we calculated the slopes, and we see that the slopes of these two families are well separated. This diagram, the histogram at the bottom. So these two families are different, and they are not they are not built of the same material, and for sure not both of them are enstatic. And here we were happy because we did we classified all our spectra in the Bas-de-Merot taxonomy, the card that I showed before, and we saw that all the objects from one family, they belong to the XC type, and the other family to the XK. XK can be either carbonaceous, can be also mesosiderite. They have been linked before with the other type of meteorites, but X's, they have been linked with enstatite chondrites, exactly what we wanted to see. For example, there was a previous study that Lutetia, because it was also one of the targets of Rosetta, it is made of this material. However, the fact that Lutetia is made of this material, so it's the same spectroscopic, belongs to the same spectroscopic type, and probably it is linked with enstatite meteorites, doesn't mean that it's also the source of the enstatite meteorites, because it doesn't have a family. We haven't seen any big impact on its surface that could capable to produce a lot of fragments and then statistically to have some falls on Earth. Okay, so you can have many objects with similar composition, doesn't mean that it is the unique source of what you have now on Earth. So now that's why we kept, let's say, as best candidate the family of Hathor. This is the grain spectrum, average spectrum that you see here. In order to find the best meteorite match, we developed a curve matching tool where we used all the published spectra of meteorites, lab spectra of meteorites, that they are in two very big databases that's called RELAB and PSF. PSF, it is in Canada. I had here a master student that made this tool, so it works actually very nice. Give us a spectrum and we find what matches. The first step gave us about 10-15 meteorite spectra that gather all together more than 95% probability to be the best matches, and this included acetate chondrites, but also some carbonaceous chondrites. So we didn't stop only in the curve matching. It's a curve, another curve, maybe you can match them, but it's not the only property that we have to take into account when we talk about small bodies. Then we did a second step where in our tool, we put also the reflectance, we compare the reflectances of the meteorites that we get from the spectrum from the lab with the average geometric visible albedo of the members of the Hathor family. To do so, however, they are both fruits, but we cannot compare apple with oranges, okay? So the absolute reflectance from the lab is not exactly the same with the geometric visible albedo. The geometric visible albedo of an object, by definition, it is a zero phase angle, but the reflex that we get in the lab from the meteorites, it is usually 30 degrees. So these two values, they have to be corrected in order to be able to compare. So we applied these corrections. We were very careful, we applied these corrections, and then then we can compare albedos with lab reflectances. And this is what you see at the plot bottom left. So we see that the Hathor family is very close to the EL meteorites. So one of the two types of the ENSA type meteorites, a bit further from the EH, actually it doesn't overlap at all. And of course, any carbonaceous meteorite that passed the first selection criterion that it was the curve matching, it is plotted here. It's even further because the albedos are very, very different. The carbonaceous meteorites are very, very dark. So we can say that we have the best lab spectrum to compare, to link with our meteorite. And then after we published, we had also the Gaia data from DR3, the visible, and we see that we more or less match our curves. Now, there are other evidence that Hathor is the source of the ELs, is the only EL that has, there is one EL meteorite that was observed while it was entering Earth atmosphere, and for that we have an orbit, and this orbit points to the fact that it comes from the inner main belt and from orbital elements from inside the family of Hathor. That's good. Second evidence is that we find EL ENSA-type meteorites in the multilithology, a very peculiar meteorite called Almahadasita. We saw it as an asteroid coming to Earth. It was a few meters long. That was 2008. They observed it with radar and so on. They went, they collected, and they saw that it was a mix of different compositions. So in order to do that, as I mentioned at my very first slide, when you have impacts of small body surfaces, impacts from other asteroids with other compositions, you bring different compositions together that they don't make sense. They cannot be formed all in the same body. So it means they are exogenous. So there should be small fragments of EL in the inner main belt where this meteorite, where the parent body of the Almahadasita meteorites came from. So there is another evidence that something was there in small fragments in order to contaminate the parent of Almahadasita. Now, the uniqueness of the match is also supported by well-established thermal models of the EL thermochronometers. So from the meteorites, we can measure this curve. So when different thermochronometers close, means when they reach a specific temperature, and indicate that these meteorites originate from the same depth of a single body. So the ELs that we have in our database, let's say, whichever EL was studied, they all show that they come from the same depth and from the same parent body. So there should be very possibly one source that gives these meteorites. So it cannot be many sources that give these meteorites. Everything points to the fact that it's one source. However, these thermal models, they estimated the original size of this EL planetesimal. How big was that when it was accreted in the protoplanetary disk? And they give that it would be between 250 and 400 kilometers in diameter, super big. But when we go and study our family, we see that the parent body of our family, then that's called Athor, that's why we name the family like that, is only about 40 kilometers in diameter. So it's very small. Then we said, okay, let's see how big was the family before the breakup, because now we see the largest fragment. So what we did is that we know that the family loses members, as I showed before. They drift to resonances. We have also collisional cascade. We have dynamical loss. So we simulate both of these processes. We also, and then add, so we saw what was the size frequency distribution of the family before this breakup 3 billion years ago. And by integrating all this volume, we saw that the original size of the EL planetesimal was only 62 kilometers diameter, only 20 kilometers diameter larger. So still very, very small compared to what they give us the models from the meteorites. So in such a small body, it is impossible to have in the heat that we need, enough heat in order to give the meteorites that we see. Because the meteorites, they have also different grades, the metamorphic grades, as we call them. Doesn't matter for now, but it was impossible. So a 60-kilometer body cannot give us these meteorites. So the question now is why the family progenitor was so small. So I have just 2 slides and I will finish. This is the resume. So our understanding is that the EL planetesimal, let's take this graph from top to bottom. The EL planetesimal accreted in the terrestrial planetary region where it suffered an initial collisional event. So it was born big, and then it suffered a collision at the early stages of the solar system evolution and fragmented it. And then one fragment, several fragments, we don't know how many, they were transported in larger heliocentric distances between 2 and 2.5 AU. It's actually where it is Athor, where is the family in the inner main belt. They were transported and then a dynamical mechanism implanted, so lower the eccentricity in order to dump it into the belt. And then many years later, there was another catastrophic collision that created the family that we see now and we characterize with our telescope. So 3 stages. We have the accretion of the small body, 300-400 kilometers, as the model show of the meteorites. We have the initial breakup, and then one lucky guy that was about 60-65 kilometers diameter managed to come into the inner main belt, where it suffered another collision and has now the parent body is about 40 kilometers plus hundreds of smaller fragments that they consist the family of Athor. Now, however, there is a question: when and under which mechanism could this planetesimal be implanted in its current location? So what is the dynamical mechanism and when did this happen? Considering now the epoch, when the same thermochronometers that the colleagues used in order to find the initial size of the parent body and so on, they show that this original planetesimal, when it was accreted in the terrestrial region, it stayed there and it needed to cool down. These are the, you see, there's a cooling curve. So it needed to cool down in order to close the last thermochronometer about 85 to 86 million years after the formation of the solar system. So this big catastrophic impact that I show here that happened in the terrestrial region couldn't have happened before this guy cooled down. So it had to happen after the 85 million years. Otherwise, it would cool more rapidly. The curve wouldn't have this pattern. This is something that people can understand if there was a collision from the cooling curve. Such a catastrophic collision, I mean, not just a cratering event. So we have more or less a time after which time, at least the earliest time that this can happen, it's about 85 million years. And now what we wanted to do, and we continue our study, is to try to understand what was the mechanism and until when, to find exactly the window. We investigated different dynamical hypotheses and carry out several dynamical simulations here with Alessandro Morbidelli in this model, the guru of dynamics of NIS, and we resulted that the only dynamical mechanism that could effectively implant small bodies in the main belt is the so-called giant planet instability. So the first cartoon up shows a profile, let's say more or less, of the solar system at the very early stage of the solar system. So we have the first generation of planetesimals, as I said, about 100 times today, from the solids of the protoplanetary disk. And then this, via collisions, they created the planetary embryos, which are bigger guys, let's say something like Ceres, something like the moon, and so on. And these guys, not bigger than Ceres, like the moon and so on, let's say half Earth, like Mars size and so on. And this, accreting more material, they created the planets that we see today, the terrestrial and the outer, the giant planets. However, the architecture of the solar system of these early phases was not exactly the one that we see today. First of all, we had 5 terrestrial planets. So apart from Mercury, Earth, Venus, Earth, and Mars, we had also a 5th planet that we call it Theia, and actually that was the planet that hit the Earth and created the moon. So the moon has some material from Theia, some material also from the Earth. In addition, the 4 giants, the outer solar system, were initially more compact and more circular orbits, and they transitioned to their current orbits via the orbital instability. So the giant planet's instability and some of its consequences, its result, they are described in the so-called NIS model. This model was developed here in NIS by the guru Alessandro Morbidelli and of course Menyos. And they had this famous papers, this combo that described this period. So we see that in the first panel, the giant planets, whereas they were 4 more compact circular orbits, and at some point Jupiter and Saturn, they enter the 2-to-1 mean-motion resonance. Then in planet B, we start to see that the orbits destabilized and they start to scatter planetesimals, all the small dots around their planetesimals, the small guys that they were still around, they were not all left. We still had planets, the planets were formed, but still we had planetesimals around, not embryos, but planetesimals. And we see that they scatter these guys is also when the Jupiter Trojans were created and so on. So this is a very important process in the very early solar system. And however, when it exactly happened is a big debate. And it's a big debate exactly of its importance in order to understand the evolution of the solar system. So now, what we did, as I said, we took our study, we took it a step further, and here I will give you the final plot where it gives all the substance of the result. In this plot, we have the time increases from top to bottom, and the terrestrial zone planetesimals, they are at the red circles that you see here. The black curve that you see in the main belt, it represents the boundaries of the inner main belt, where objects actually exist today. So in our work, combining the meteorite thermochronometers that we had from the literature with dedicated dynamical simulations, we saw that this instability, it planted planetesimal fragments from the terrestrial zone into the inner main belt at least 26 million years after the solar system's beginning. And then now, as I said, this is the lower limit. The upper limit for the instability has already been given 2 years ago by colleagues from Sweden in Boulder, that they set it up to 100 million years after the beginning of the solar system due to the presence, I won't go into details, due to the presence of binary asteroids that they are captured as Trojans around Jupiter. Therefore, our work here tightly constrains for the first time when this instability happened, because it was a big debate. At the beginning, they said it was some 100 million years after the beginning of the solar system. This created also the lunar cataclysm. Finally, there is no lunar cataclysm, so there is no late heavy bombardment. This instability should happen the first 5 to 10 million years after the beginning of the solar system, but this cannot explain some other stuff. So now we came with an age that it is more reasonable, and also we are very happy with that because it comes directly also from observations. So it's not blind modeling. We use really observations in order to constrain this thing. So by linking a little piece of meteorite to a source and study all the physical properties, we can understand the sequence of events, and then this can give feedback to this dynamical models. Here we have to say that the moon forming event happened more or less as time, around 100 million years. So the instability very possibly triggered the formation of the moon. So Theia was there still around where all this happened, and it has been shown by other studies that just maybe 10 to 20 million years after the occurrence of the giant planet instability, we could have the lunar formation event. So that's a very interesting period to study. We hope we had some good reviews from that. We should receive them any day now. In order to do this big job, we had to develop a database of physical properties of small bodies that was developed here in Nice, a national service here in France. We have data for more than 1 million asteroids, and we have all the properties that I mentioned before. And now we are collecting, and we start to prepare an extension of the database in order to have also spectroscopic observations. So we really collect all the processed material from the colleagues, from the PDS and so on, and we try to put them in a correct order and give them publicly available to people. Of course, here we include only published works. We don't take anything from telescope repositories, and we are against doing these things to colleagues. First, someone has to publish, then we can take it and we give it some more visibility. And this can allow us to perform studies that involve thousands of objects when we need the physical properties of thousands of objects to study a family or to study a specific location in the belt, and so on. So this is what I would like to present you today. So we had the meteorite, we found its source, we know where it is in the main belt, and this specific material was born in small heliocentric distances around here, around 1 AU, and Earth accreted this material. We are double happy. And now we managed to put a third point in this plot. So apart from Obrites and the HEDs that are linked to Vesta, we have now the Hel.A.S meteorites that they are linked with the asteroid family of Hathor. So we are super happy also for that. We put one more little stone to this puzzle. Thank you very much.
Thank you, Chrysa. So are there any questions for Dr. Avdellidou? Please raise your hand or turn on your mic. Okay, John.
Sorry, I just accidentally unmuted myself. I'm sorry.
Okay. Well, while people are...
But great talk, and thank you, Chrysa, for this overview.
Was it understandable?
Oh, absolutely.
Very much, yeah.
Okay.
Absolutely.
Yeah, thank you. It was a very clear talk. So while people are preparing their questions, I have one.
Yes.
It's a bit tangential to your work, but since I'm very far away from this field, I always was wondering, are you aware whether there are any evidence, spectroscopic or from the missions that have visited these small objects, of the presence of organic material on the surfaces of these objects?
Yes, thank you for the question. A lot. Okay, the problem with the organics is that usually we observe it about 3.5, something like that, microns. Generally, the water, the hydration and the water content, hydration you can have at 0.7, you can see from the ground, then you can have a 2.7 to 3.1, where you can see also some ice, but is where you have also the telluric absorption from the earth, so it's not the best thing to do from the ground. Then you have the organics around 3.5, something like that. I'm not studying specifically organics from that, but it's around there. So we don't do that from the ground, but the space missions have done that. So they have seen organics both on Bennu and Ryugu, so the two dark primitive asteroids, and we expect actually to see their organics because they're more primitive. They come from the larger heliocentric distances. They had they were ACOs altered, so it means they had some at some point water and so on, not water now, liquid that you can see it. So yes, they have seen organics, and actually it was a combo of beautiful papers. They were published in Science from the return sample of Hayabusa 2 from Ryugu, and they found also macromolecular structures, organics, and so on. So they have a plethora. And also, I think the Dawn mission, they found some aliphatic, they have also some salts, and so also they have also some ideas about Ceres, the largest asteroid, let's say, that we have now in the belt. But definitely the sample return, they have found. And now we are waiting for Bennu, the other one, but it will come in the NASA one. It will come in September. It will land.
Very exciting.
Yes. And we will see now there are the missions. They will go to the moons of the outer of Jupiter. We have JUICE, also we have MMX. MMX will go to the Martian moons, where we can see also, they will be able to detect if they have organics, because the spectrometer reaches these wavelengths. So we will see.
Yeah. Thank you, Chrysa. So are there any other questions for Chrysa? Okay, if not, thank you again for giving this very clear talk, and thank you everyone for coming.
Thank you very much.
Have a good evening.
Thank you. Bye-bye.
Bye.